We've talked about work in this unit, but now we're going to talk about the relationship between work and energy. And energy is the ability to do work. In the work equation that we have on our AP Physics 1 equation sheet, we see there's a relationship between the change in energy being equal to work. We will talk about that more later. This is the work-energy theorem. For now, I want to introduce the idea of energy and the types of energy. So the two main categories I'm going to talk about are kinetic energy and potential energy. Kinetic energy is the energy of motion. Anytime something's moving, it has kinetic energy. And the equation on your AP equation sheet is that kinetic energy equals 1/2 times mv squared. M is the mass given in kilograms, v is the velocity given in meters per second, and when you take kilograms times meters per second and then square the meters per second, you get a unit of joules for energy. That's the same unit that we used for work, and that's because work and energy are related to each other. So let's give a simple problem. Let's say we have a 625 kilogram car traveling at 18 meters per second. What is the car's kinetic energy? All we need to do is plug those numbers into the equation for kinetic energy, and we get the kinetic energy of the car is 101,250 joules. The other main category of energy is potential energy. This is stored energy. It's not from movement like kinetic energy. It's stored energy of position. And there are a couple of different types of potential energy. We're going to focus mainly on gravitational potential energy. The two main types are gravitational potential energy. This is the energy you have from having height. So this roller coaster, just by having height, has stored energy. And it will fall down because of that stored energy changes from the gravitational potential energy into kinetic energy. So gravitational potential energy comes from having height. We also have elastic or spring potential energy. When we use a bow and arrow or a spring, we have a stored energy in that we can release and change into kinetic energy. We'll talk more about elastic and spring energy in a later lesson. But let's look at gravitational potential energy. And this is when we're looking near the surface of the Earth. We're going to use G as 9.8 meters per second squared. This person up here has a height, so they have gravitational potential energy. And when she gets down to the bottom, she doesn't have gravitational potential energy anymore. This is a simple equation for gravitational potential energy. U stands for, or U sub G. This U is energy, and then the subscript tells us it's gravitational potential energy. It's equal to the mass times gravitational acceleration times y, which is the height of the object over the surface of the Earth. Now this is not the equation that you see on your equation sheet. What you see is this equation. Delta UG equals mg delta y. So very similar, but this is just looking at the change in gravitational potential energy, not just what is it at one point. And as a reminder, delta means the final minus the initial. So for example, delta y equals final y position minus the initial y position. So delta UG, the components of it are the change in gravitational potential energy equal to mass times gravitational acceleration times the change in the height. So let's do an example. Let's say, what is the change in gravitational potential energy for a 30 kilogram girl here going down a slide? What's her change in energy? We're going to use the equation change in gravitational potential energy equals mg delta y. Remember that delta y is yf minus yi. Plug in your values, mass, gravitational acceleration, final height, which is 0, minus initial height, and we get a change in gravitational potential energy of negative 2,646 joules. Now it makes sense that this is a negative number because she's gone from a height of 9 meters down to 0. She has lost her potential, her stored energy. So her change is going to be negative. Her energy has gone down. Now let's take these two main categories, potential energy and kinetic energy, and combine them When we take those two types of energies together, it gives us the total mechanical energy. These are types of mechanical energy. So we say the total mechanical energy is equal to the kinetic energy plus the potential energy. So in a perfect world, energy is conserved. Well, in reality, energy is conserved. It's just that oftentimes we can't measure the loss of energy because it goes to friction or heat or sound. Well, let's talk about an ideal system where all the energy can be accounted for, and it's all going to be kinetic energy or potential energy. So we're looking at only internal forces. We're not applying a force from the outside. We're looking at conservative forces, and we're going to talk about that in a later lesson. So basically, we're going to ignore friction. If only internal conservative forces do work, then the total energy is conserved. So if we ignore friction, we ignore heat, we ignore sound, we can look at the conservation of energy. When energy is conserved, that means that the sum of the kinetic and potential energy is going to be the same, meaning the energy that we start with equals the energy that we end with. Now, some of the energy may change from one form to another, but the total is not going to change. So this says the initial energy equals the final energy. And remember, our total mechanical energy is our kinetic energy plus our potential energy. So our initial kinetic energy plus our initial potential energy equals our final kinetic energy plus our final potential energy. And all this is saying is that the energy at the beginning of some process is equal to the energy at the end. Now note that these equations are not on your equation sheet, but the basic idea is that your energy at the beginning equals your energy at the end. So if we're only looking at the force of gravity, which we are in this lesson, this is a conservative force. If it's the only force, then we can take these equations and we can use the other equations for kinetic and potential energy, and we can basically say our initial kinetic energy is equal to 1/2 mvi squared, where this is our initial velocity. Our initial potential energy is mass times gravity times our initial height. Our final kinetic energy is 1/2 mv squared, where v is our final velocity, and our final potential energy is m times g times final position. So let's look at an example. Let's say we have a skier who's going down, and then she's going up in the air and back down. We want to know what is the total mechanical energy at each point in the sequence, and is energy conserved? So first, we can look at this first section. Total mechanical energy is her kinetic plus her potential. It's 50,000 joules. Let's look at the second point. Her total mechanical energy is still 50,000 joules. The third point, we're going to add her kinetic energy plus her potential energy, and it's 50,000 joules. At this peak, we're going to add our kinetic energy and potential energy, and we get 50,000 joules. And at the bottom, we're going to add her kinetic energy plus her potential energy, and we get 50,000 joules. So what's going on in this? She starts at the beginning with no kinetic energy. She's not moving. All of her energy is stored. As she goes down, some of that potential energy changes into kinetic energy. So now she has a little bit of kinetic energy and a little bit less potential energy. Down here, she has even less potential energy and more kinetic. Then she goes back up to the same height. Now she has kinetic energy of 20,000 and potential energy of 30,000. When she gets to the very bottom, she shouldn't have any more potential energy because her height is 0. And she should have all kinetic energy. But the sum of energy didn't change. Even though it changed from one form to another, the total mechanical energy stayed the same. So is energy conserved? Yes. The total mechanical energy is conserved. It doesn't change.